Okay, chapter 10. Once again, new life. We move on from solids to fluids. And I'm pretty sure you know that there are three phases of matter: solid, liquid, and gas. In fact, there are four phases because there's also plasma, which is ionized gas. But physics of plasma is a different story. It's the whole science on its own. So, not talking plasma. But liquids and gases are fluids. I'm pretty sure you didn't know that when you say fluid, it's not just liquid, it's also liquid and gas. Uh, and of course, you have some different parameters for liquids and gases. You can do rotation of of any of that because it was rotation of a solid object. Now it's fluid. You don't do uh, you don't apply torques to that, right? So definitely we need new parameters and uh, different types of the flow of a fluid we'll discuss, and you'll see for yourself how everything changes once you go from laminar flow to turbulent flow. Good news, we're not going to do any turbulence here because it is still somewhat a mystery. It's hard to explain many turbulent flows, especially if it's a swirl flow and all of the other conditions on top of that. So none of that. Just the laminar flow, just the equation of continuity and Bernoulli equation, which is your conservation of energy principle for fluids, and that's pretty much it. So no more solids, focusing on liquids and gases. How do you know it's a liquid? Well, liquids have fixed volume and can be of any shape, and gas can be of any shape and can easily be compressed. This is the major difference between a gas and a liquid. You can easily compress a gas and change the volume. For liquids, at least the models that we're going to discuss here, the ideal liquid, it's incompressible. So no compression for liquids in this level of physics. Both liquids and gases flow, and they're called fluids. So fluids are all the substances that can conform to a container and can flow freely. And of course, physics of fluids is your bread and butter into if you are into hydraulic engineering. It's a huge branch of engineering. Now, remember we discussed statics last chapter. That was your building, construction, and everything that deals with producing different shapes from solids. Now for fluids, it's definitely a way to discuss hydraulic engineering. So all the pumps, all the tubes, the physics of flow of, say, blood in your veins, all of that is governed by Bernoulli equation, for example, and equation of continuity. So a lot of applications, a lot of things to keep in mind if you're into hydraulic engineering. So let's discuss the first basic parameter, which is the density. We already did some calculation. We did some calculations of densities before. For fluids, fun fact, it's the same thing. It is the mass with respect to volume. The units are still kilograms per meters cubed. And that's a scalar quantity. You can't really assign any direction to density. So density is just what you see in a table and use for certain calculations. If mass is not given, but volume is given, or volume is the unknown parameter. So you can easily use this definition to figure out the missing pieces of a puzzle. One thing that, like one specific fluid that I want you to keep in mind at any time is water. Water is the most common element that you deal with in hydraulic engineering. So density of water, approximately, it's not exactly 1,000, but it's approximately 1,000 kilograms per meters cubed. Consider that given at any moment of time, even if it's not given specifically in the problem, you still have to consider 1,000 for density of water. And specific gravity is something that we'll never use in problem solving, so you don't have to worry about this ratio of density to that of water. It's just the density of water by itself that we're going to need for problem solving activities. So density of water, about 1,000. And if you really want to go into details, the density of ocean water is has a little more of a value. It's like 1,030, 1,050. And if it's just fresh water with no salt in it, then it's going to be a little less. And that's why we got icebergs that are floating on top in the oceans, because the density of iceberg is just the density of just fresh water rather than density of seawater. The second major parameter for fluids is called pressure. And pressure is defined as a certain force that you exert in a unit area. So the units would be newtons per meter squared. But we have a very famous scientist, Blaise Pascal. You probably heard about Pascal's triangle in mathematics and other things in science that are called with Pascal's name. So we have a tribute for Pascal in physics. The SI unit, the System International Unit for pressure, is officially 1 Pascal. So Pascal's is what I expect from you rather than Newton per meter squared, which is exactly the same thing. Atmospheric pressure, we live on planet Earth, on the surface, on the surface of Earth, and there is atmosphere made of air, which is about 75% nitrogen, 21% oxygen, and then the remainder is argon and other gases. So that's gases. Those are fluids, right? Remember, fluids are liquids and gases. So atmospheric pressure from the air that surrounds our planet is approximately 100,000 pascals. So see how it's not exactly 100,000, it's 113,000. I will not penalize you if you'll just say 100,000. So 1 times 10 to the power of 5, that's perfectly fine. The discrepancy is only 1%. So if you'll just say 100,000 for your calculations for atmospheric pressure, that's perfectly fine. Also, there was another guy, Torricelli, who invented the barometer, and that's why you will sometimes see units that are called torr, and that corresponds to 1 millimeter of mercury. Inside a manometer, that's not System International. Don't do torrs, don't do bars. Make sure you always talk in terms of newtons per meter squared or pascals, because Pascal is defined as Newton per meter squared. And in the United States, of course, everywhere is PSI, the pound per square inch. Well, nobody else uses that. So if you want to do physics, if you want to do research, forget PSIs and make sure you always convert to pascals or newtons per meter squared. Fun fact, see how pressure is force per area and force is a vector. And you might say, hey, pressure should be a vector as well. But it is not, because it's going to be the same value regardless of orientation. And Otherwise, the fluid would just flow. And for a fluid that is sitting still, you can think about any direction. Any direction is good for figuring out the pressure at a certain point, at a certain depth. So static pressure is scalar. No need to draw vectors for figuring out the pressure, okay? Later on, we'll discuss the buoyant force. Well, that's a force. Forces are vectors. But if the question is for pressure, you don't have to show any direction for pressure. Also, if the fluid is at rest, there is no component of a force parallel to any solid surface. You can see that the water is not going up the bottle, even though you can see sometimes, like in real life, you will see the surface tension forces. We're not going to discuss any of that. Real fluids are real, but our fluid is ideal, so do not think any surface tension whatsoever, not at this level. So atmospheric pressure is 100,000 pascals. And you might say, hey, that's a lot of newtons. So how in the world are we not crushed by this huge force? Well, the answer is easy. We are made of cells, the body is made of cells, and the pressure inside the cell, guess how much it is? That's correct, 100,000 pascals. So you have 100,000 outside of a cell, and you have 100,000 pascals inside the cell. So the outer pressure is counterbalanced by inner pressure. So outer force coming from the atmospheric pressure is counterbalanced by the force from within the cells. So we are perfectly fine. We have evolved to a condition where our bodies are suited for atmospheric pressure. We don't need to worry about that pressure crushing us. So guess what's going to happen when you step outside of a spacecraft with zero pressure? Our body could easily just blow up because of the pressure of cells that we are made of. So be careful. You always need the space suit that maintains the pressure around your body at atmospheric level. Another example, the dealing with atmospheric pressure is when you are inside an aircraft and you fly to, say, I don't know, Australia or Europe, like a long flight, and you step outside of aircraft, the destination airport, and you feel extremely tired, like you want to die. It feels like you ran a marathon or something, and you wonder, why in the world are you so tired? Even though you were sitting for the last, like, I don't know, 10 hours. What's going on with your body once you step outside the aircraft at the destination? The answer is easy. The aircraft does not provide you with exactly atmospheric pressure. Many airline companies only provide you about 70-75% inside the cabin. And the difference in pressure is what really makes you sick. So next time you're on an airplane and you're completely exhausted after that flight, it's not because, like you did some work or whatever, like you exercise or whatever. It's just the lack of pressure in the cabin that just your body reacts to that, and just you're extremely tired, you get sick, and it takes some time for you to recover with the atmospheric pressure around you. Okay, so pressure is force per area. What kind of a force? For a fluid, that would be the gravity from the top layer of a fluid acting, pushing against the bottom layer. So it is the gravity of all the, say, water in this glass cube that pushes on a certain like bottom layer in the same cube. So gravity is mg over a, and you can recall that mass enters, where's the formula? Mass enters the relationship between the density and the volume. So what is mass? Mass is density times the volume. So every time you have mass in your formula for fluids, you can replace it with density times the volume and see how volume is also the cross-sectional area times the height. Area cancels, and you're left with a very important solution for calculating the pressure. You can see that pressure at a certain depth is related to the density of the fluid, G, which is 9.8 for this planet, for the surface of this planet, and the depth. See, H can be the height, the altitude, or it can also be as a depth, so certain depth. The deeper you go, the more the pressure you experience. So any liquid whose density doesn't change with depth, you have this connection. So P is rho GH for static conditions, for static fluid with no motion. You will always get this connection, and you can solve a lot of problems with this little relationship. Okay, next is atmospheric versus absolute versus gauge pressure. So all sorts of pressure that you can come across. This is the most general formula that connects them all. See, the previous formula was just rho GH. So this is the pressure at a certain depth. Like the deeper you go, the more the pressure increase you see. But let's not forget that it's not just the pressure from the fluid. You also have the atmospheric pressure on top of that fluid. You have some fluid in a container, and what's on top of that fluid is atmospheric pressure, the 100,000 pascals that you can't ignore for all of your problems. You have to remember that there is atmospheric pressure if you're solving something for planet Earth. If you go to the moon, of course, then there's no atmospheric pressure, and you don't have that parameter to worry about. But on planet Earth, we distinguish between absolute pressure, atmospheric pressure, and the hydrostatic pressure, the additional pressure from the fluid. You can see that absolute pressure is the sum total between the hydrostatic and the atmospheric pressure. So this is just the terms. Read the question on what is the unknown parameter. If the parameter is just what is the pressure at a certain depth, then it's just your hydrostatic pressure or GH. But if it's like a system of tubes that exchange fluids back and forth, then you definitely have to remember that there is atmosphere on top of the fluid. So absolute pressure is probably what you'll be looking at. So the difference between the absolute and the atmospheric pressure is also called the gauge pressure. Sometimes people say gauge, sometimes gauge. I've heard both pronunciations. I say gauge. The idea, once again, is that if you don't want to include the atmospheric pressure, then you just say gauge pressure. If you want to keep in mind the atmospheric pressure, think about absolute pressure. So here's a little quiz 4 containers with oil. It doesn't matter, olive oil or sunflower oil or any other oil, just the same substance that you pour in those containers. And you have to rank them according to the pressure at a certain depth H. So that's the surface level, and H is the same for all of the containers. So greatest first. The common misconception is to say that, say, the more fluid you have, the greater the pressure it's going to exert, which is a mistake because the formula says what? It's the density of the fluid. The pressure depends on the density of the fluid, the free fall acceleration, and the depth. So free fall acceleration is the same. Fluid is of the same type. You have density of oil here, density of the same oil there, density of here, and density there, all of the same densities, because density is a parameter that doesn't change, and you can just look it up in a table, and that's it. It's a constant thing. And if the depth for all of those containers is the same, if H is the same, then everything is the same. Density is the same, G is the same, H is the same, so pressure at a certain depth would be the same. All the pressures will be the same because it's just the density, free fall acceleration, and the depth that the pressure depends on. Okay, just a brief introduction to Pascal's principle. It is the main idea that governs the transmission of pressure through the fluid. The fluid should be incompressible, and if external pressure is applied to one side, then it will be transmitted within the fluid everywhere, and there will be the same increase from the other side of a tube, for example. So if you're thinking hydraulic lift or hydraulic brakes, the answer to the main principle is the Pascal's principle. You create a little bit of a push from one side of a piston, and then that pressure is transmitted all the way through the tubes in the pump, and then an equal but opposite reaction would be the result of the Pascal's principle on the other side of the tube. Let me show you the diagram. The diagram really has it all. For a hydraulic lever, the device that can lift up your car easily, you do that boom, 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 boom on one side, and then all of a sudden your car magically is lifted, and the car has quite a weight, right? You can't lift a car with bare arms. There's just no way you can be that strong, right? So let's see what's going on here. The idea is, once again, that if there is a change in pressure from one side, then all that change would be transmitted to the other side, and there will be a change on the other side. So let's see what kind of a change we're talking about. Well, what is pressure? Pressure is force per area. So the force that you exert on a piston on one side will be proportional to the force that you will produce on the other side of the hydraulic lever. And the coefficient of proportionality is the ratio between the areas of pistons. So if the inner, the small piston, it's easy to compress it to a certain state, the pressure on the outer side would be much greater because the area of the outer piston must be much larger value. So the more the difference between the areas, the cross-sectional areas of pistons, the more the increase in the force you will experience, even though the pressures are the same. So once again, change in like extra producing extra pressure from one side, you get that same extra pressure on the other side. And with the ratio of forces to cross-sectional areas, you can produce infinite force. It can be infinitely large if the ratio between cross-sectional areas is infinitely large. So a very straightforward demonstration shows you the power of Pascal's principle. You can lift up not just a car, you can lift anything. Just make sure the piston can withstand that pressure and you're good to go. Now, how do we measure pressure? How do you know that it's more than atmospheric pressure, it's less than atmospheric pressure? The simplest device is what we call man. And let's do just the basic open tube manometer. You have a U-shape tube that you connect to a tank with the unknown pressure of a certain gas. And then there's a liquid with a certain color that you can easily recognize, you can easily see. And the idea here is that at the same level for that fluid, you should expect the same pressure. And from one side, it's the atmospheric pressure and the hydrostatic pressure caused by the fluid on one side of the U-shaped tube. And from the other side, it's going to be the pressure that the tank with gas pushes the liquid with. And once again, the pressure at this level is the same. So if you can measure the rho GH caused by the fluid here, and you know what the fluid is, plus the atmospheric pressure on top of the fluid, you can easily tell what is the pressure inside the tank with that unknown gas. So pressure is the same. Don't forget that there is atmospheric pressure, and then you just have to do the atmospheric pressure plus rho GH, and you will figure out the pressure inside this tank right away. Yeah, so rho GH, which is H is the difference between the levels. You have level 2, level 1. So change in the vertical level plus the atmospheric pressure, that's what gives the pressure on this level. From one side, it's the pressure from the gas tank. From the other side, it's the pressure caused by atmosphere and the fluid inside the manometer. Yeah, it can be positive or negative. There's easy case when, okay, I don't have the case here, but I have a problem that deals with both cases. It can be the upside down. This fluid can go all the way up, and this level will go all the way down. That will tell you that atmospheric pressure wins against the pressure in the tank. So what's going on in the tank is going to be less than atmospheric pressure. So just by the level of a fluid inside a manometer, you can tell if it's more than atmospheric pressure and by what amount, or you can say that it's less than atmospheric pressure if the fluid is upside down and it's lower in the right tube and higher in the left tube. Another clever device invented by Mr. Torricelli, that's why you have the Tor thing, is the barometer. And barometer measures atmospheric pressure. Your best bet is to measure the atmospheric pressure, which changes with weather, of course. You have daytime temperatures, and the pressure is higher because temperature is higher. And then nighttime temperatures, and pressure drops. And if pressure drops, then wind is going to be blowing towards the lower pressure zone, and you can get clouds and precipitation of any kind. So measuring atmospheric pressure pretty much allows you to predict weather, and very important, parameter to do, all sorts of physics experiments, for example, or other activities. So what you have here is the upside down tube, which is immersed in a certain liquid. That liquid is most likely mercury. You can do other liquids, but mercury would be the best bet for being the compact size. And what's going on here is, if there is atmospheric pressure outside and you create zero pressure inside the tube, then the liquid will be pushed towards the lower pressure zone. So the liquid will actually go into the tube and stay at a certain level. And for conditions of just normal atmospheric pressure and the fluid being mercury, you will see the value of exactly 76 centimeters of height inside this tube. So if the fluid is mercury and pressure, atmospheric pressure is normal, it's not high or lower than normal, then you will measure exactly 76 centimeters of a level. If atmospheric pressure is a little less, then there's less force acting on the fluid to get into the tube, so the level will drop. If atmospheric pressure is greater than normal, which is usually the case for California, you know how California, we're famous with a lot of sunshine, sunny days, because it's constantly higher pressure than in neighboring regions and states. So our Sunshine State is famous for its high pressure. The pressure is higher than normal, and that's why you have much less precipitation. Precipitation happens where the pressure is low. So if the pressure is higher than normal, then the level of mercury will go up, and you will see that in your barometer right away. So with that, here comes the fun fact that you think that it's you who pulls the soda up the straw, but in fact, it's actually the pressure that pulls the straw, that pulls the soda into the straw, because you do the sucking of air, from the straw, you create this zero pressure inside the straw, and the fluid goes into the straw because atmosphere pushes it downward and into the tube. So it's the change in atmospheric pressure, it's change in pressure between the atmospheric pressure and the pressure inside the tube that creates this force that forces the fluid into the straw, and you can enjoy that cold drink on a sunny day. So your barometer is pretty much the same principle as you trying to suck some Dr. Pepper into your body, and you create that zero pressure inside the straw, and the fluid goes into the straw because of a change in pressure. Okay, on to the buoyancy and Archimedes principle. Archimedes principle is our next lab after the ballistic pendulum, so you definitely want to pay attention for this section in particular. I'm pretty sure you've noticed the buoyant force in your life. I'm pretty sure you used to swim in a swimming pool at some time. Even if you are not into swimming, I'm pretty sure you at least tried swimming. And you probably noticed that you will sink eventually if you don't breathe, if you don't, push or pull with your hands and legs. But there is still some kind of a force that prevents you from just free fall sinking into the swimming pool. There's like a force that tries to pull you up and brings you up inside any kind of a fluid. In fact, buoyant force acts on you right now because you are submerged into air. There's air everywhere around, and air is fluid. So every time a certain object is submerged into a certain fluid, there is buoyant force. There is Archimedes force. You call it Archimedes force or buoyant force, doesn't matter. You can do both. So why is there a buoyant force? What's the reason for that force to appear and be present for all the objects that are immersed in a certain fluid? Let's take a look at an object. That's this yellow object submerged completely into a glass of water. What do we have for forces acting on the top versus the bottom layer of the top and the bottom part of the object? Well, there is a force pushing it down versus the force that is pushing it up. And fun fact, buoyant force is always upward force. So why is that even the case? Why is there even any net force that you can get? The main idea is that pressure, remember how pressure is always, any kind of pressure depends on the depth. So the deeper you go, the more the pressure. And what is pressure? Pressure is the force. So the more the pressure for the same cross-sectional area, the more the force you get. So there is pressure at this level, right? And what kind of pressure is that? It's going to be rho GH sub 1. And what kind of pressure would you get at a level that is deeper into the fluid? Well, the different depth, H sub 2, and it's rho GH sub 2 now. So which force is stronger? Of course, it's the one where the pressure is greater. So greater pressure, deeper level, like more depth, and you get more force acting on the bottom of this yellow object. So force is greater. That means that the F sub 1 is not that great. So overall, F sub 2 acting on the bottom surface of the object wins versus F sub 1 that acts on the top part of the object. So pressure at the top is less than pressure at the bottom. Therefore, the force at the top is less than the force at the bottom. So change in forces, difference in forces, that's the net force. This is your idea of a net force behind. And this is the net force that we call the buoyant force. This net force is the buoyant force acting on the object. So it's always upward because the force at the bottom is greater than the force at the top. And you can easily calculate it from just basic definitions because we said, hey, pressure is force per area. So if you want the force by itself, then it's pressure times the area. Pressure times the area, and you get the force. Pressure times the area, and you get the force. Pressure times the area, and you get the force. So difference in forces is the difference between pressure times the area. Area is the same. Let's say it's the same, say, cylinder, and there is a cross-sectional area of a cylinder, which is a circle, pi r squared. It doesn't matter what kind of shape it is. It's going to be the same area for the top and the bottom. So we're going to factor out the area, and pressure is rho GH, and we know it's the same fluid. So fluid goes outside of the parentheses as well. It's the same G for both forces, so G also goes outside of the parentheses, and it's only the change in depth. So h sub 2, take away h sub 1. This is your delta H, the change in the depth, that really plays the role in determining the buoyant force. So buoyant force depends on the fluid. Be careful, it's the fluid, the density of a fluid, not the object, times the free fall acceleration, times a certain geometry for the object, and the change in depth. Now, what you will see in most problems is the backward conversion from area times the depth. You will replace it with the volume, because if it's area times the height, it's the volume. And what you can think of is the volume of the submerged portion of the object. If it's completely submerged, then this submerged portion will be the total volume of the object. But it's not always the case. If that object is floating on top and half of that object is above the level, then the submerged portion will not be the total. It's only going to be a certain part of the object that is submerged. So be careful with your subscripts. For the buoyant force, it's the density of the fluid, not the object, and only the submerged part of the object. If for some reason you want the total volume, then you're going to be talking about the density of the object, and that would be the total mass over the total volume of the object. This is a very common mistake when people just say rho GV, but they will never use correct subscripts, and they make mistakes because they don't know what they're talking about. For the buoyant force, once again, it's the density of the fluid and only the submerged part of the object. Sometimes it's completely submerged and then it's total, but sometimes it's not completely submerged and you will get just a fraction of the total. And as long as it's density times the volume, you can think about some kind of a mass, but this mass is tricky. This mass is not the mass of the object. It's the mass of the displaced fluid. It's the mass of the fluid that was displaced by this object, which is a little bit confusing probably. So if it is confusing, if you're not getting the idea of this misplaced fluid, just don't even bring it on the table. Just use the density of a fluid times the volume submerged, and you'll be in a good shape for all your problem-solving activities. We'll solve some problems. You'll see how this works. So first of all, if there is some kind of a fluid and an object is submerged into it, there is always a buoyant force. What's so special about this force? It's always upward. It's always in a certain direction that is trying to pull the object out of the fluid. And it opposes the weight of the object. And remember how weight it would be downward, and buoyancy opposes that direction. And the only source for this force is the change in pressure with the depth of fluid. So first case, when the object has less density than the object than the fluid. Let's say fluid is water. Let's say 1,000. We already know that density of water is 1,000 units, kilograms per meters cubed. And let's say we got wood, something made of wood. And if you look in the table, you'll see that the density of wood is about 6, maybe 700 kilograms per meters cubed. So density of wood is less than density of water. I'm pretty sure you noticed that wood usually floats on top and never sinks. And that's exactly the correct statement to say. Why is that so? Why does wood never sink? Why is it always floating on top and it's not completely submerged? It is because the buoyant force is greater than gravity. Buoyant force wins over gravity. Buoyant force is what? Density of a fluid times g times the submerged portion. And gravity is just mass of an object, which is density of wood and total volume of the object. And g will cancel on both sides. You will see that the left side of the equation wins over the right side. So upward buoyant force is greater than gravity. It forces the wood to accelerate upward, and eventually wood ends up on top up until a certain portion is not submerged, and then it goes into balance. It's in equilibrium, and you will always see a piece of wood on top of the surface of water. So for this condition, we call it floating. Every time something's floating, it means that there is equilibrium, there is balance of forces. So your buoyant force is completely balanced by the force of gravity. And the buoyant force is the density of a fluid once again, volume displaced. See how volume displaced would be just, in this case, about half of the total volume times the g versus the gravity. Gravity refers to the object, so it's the mass of the object, so it's the density of the object, and the total volume of the object. See the difference? It's not the fluid anymore, it's the density of the object. It's not submerged part, it's the total volume. But if it's floating, you set them equal, g cancels on both sides, and you can solve for many different things that are missing versus what's given. So this is a very common scenario to solve problems for floating. In fact, I really want you to show me this kind of a setup for all the floating conditions and set those two forces equal to each other, because buoyancy is up, gravity is down, so one is positive, the other one is negative. But if with no acceleration, you just set them equal and solve the algebra for what's missing. And then hot air balloons, the perfect example when you can beat the gravity and actually keep on going up. What do you get? You get buoyant force being, see how the arrow for buoyant force is much greater than both gravities, and buoyant force can actually cause some acceleration. Even if there is no acceleration, there is still your buoyant force being up, gravity of a helium that makes up the hot air balloon, and then some load that you attach as extra load to your hot air balloon. Worst case scenario, it will be just a constant velocity, upward direction. The change in density between the helium and the surrounding air, or if it's just air balloon, then hot air has a winner versus cold air, and the hot air balloon rises up because density for hot is less. Oh, have you ever noticed how it's always hotter on the second level in a house versus the ground level? Ground level is always cooler. Why is that so? Because hot air has less density and it rises naturally, upward. And all that hot air is going to be found on the second level or third level, and the ground level is going to be cooler just because of this natural, we call it convection. So, hot air balloons or helium balloons, there is a huge buoyant force because of the change in density, and buoyant force wins over gravity. You can do a lot of crazy stuff with it. Well, also a problem for that in a classroom discussion, so stay tuned for that. Some questions to address. We've got a penguin, and penguin floats. So the key word is floating. Floating means what? Floating means equilibrium. You have a balance between buoyancy and the gravity. So penguin floats, and then at first it's fluid of density rho sub 0, just some random number. Then it's a density of 0.95, so less of a density. And then in a fluid of some more density, so 5% less density, 10% more dense fluid. Rank the densities according to the magnitude of the buoyant force. So how do you compare the buoyant forces if the density of the fluid changes? Well, this is a trick question because your first bet would be what? Oh, if density is different, then the force should be different, right? You have density of a fluid changing, and you would say, hey, force, buoyant force has got to be changing. But that would be forgetting the key word, which is once again what? Floating. Floating conditions, it means it's equilibrium. Your buoyant force is equal to gravity. And what do you say for a gravity of a penguin? We do have some change in density of a fluid, but the mass of the penguin stays constant. We don't do anything to a penguin. And it's the same G, 9.8 for planet Earth, which also stays constant. So the product, mass times the free fall acceleration, stays constant. The weight of a penguin stays constant. And if the penguin is floating, then the buoyant force must be exactly the same as gravity. And if gravity doesn't change, then buoyant force will not change as well. So the forces are all the same because of the same gravity of a penguin. And you might say, okay, I understand it, but still, what do we do with that fluid? The density of the fluid changes. How in the world the force is the same? Well, because it's not just the density of a fluid. There is also a G, which is constant, but there is also the displaced volume. Okay, so you're playing with densities of a fluid, but that will result in a change in the displacement, the volume of displacement, the submerged volume. So more density, less volume submerged, and vice versa. Less density, greater volume, so that the product stays the same. So be careful with the word floating. Floating is equilibrium, and if gravity doesn't change, then buoyant force must be the same in all scenarios. And it's two things to consider that can change. Either the density of a fluid, if you change that, but then it's going to be the volume displaced or volume submerged. There's going to be a change in that parameter as well. Okay, same question, but now it's the amount of fluid displaced by the penguin. And I just said that, yeah, the buoyant force stays constant, but buoyant force is not just the density, it's also the volume displaced. The submerged part of the object changes. And with more density, you get less volume. More volume, less density. That's exactly what the question says. Less density, more volume, so less density, greatest first for the amount of fluid displaced, greatest volume submerged. Everything is this way because there is floating procedure. The key word is floating. If there is floating, everything is in equilibrium. Okay, one last like big chunk of information for fluids is motion, so dynamics. Remember, it was all static, right? We had static, no motion here. We had static for hydrostatic pressure, right? Hydrostatic, static, right? Now we're moving on to dynamics. We move on to motion. And motion of real fluid is super duper complicated, and in many cases it's very poorly understood. We do have some models, we do have some connections, but overall, for fast-moving fluids, we have more confusion than explanation. This would be one of the areas that you can do your own research and become famous and give us more details on those turbulent flows. We're not going to do any turbulence for this class, don't worry, and it's not real fluids. The fluids are going to be ideal, which will simplify our problem-solving procedure. So only laminar flow is considered. See how everything is a smooth and steady flow. Nothing like this. This is your turbulence. See how the flow breaks up, and you see those artifacts, if you will. You see those disturbances, inconsistencies, and those swirls. Once you go into those swirls, everything becomes chaotic, and it's really hard to build a good model for such flow of a fluid. So nothing turbulent, only the laminar flow is considered for our problems. And for laminar flow, we have to define what we call mass flow rate. It is the amount of mass that passes through a certain cross-sectional area in a certain interval of time. And remembering that mass is density times the volume, and density stays constant. You don't change the fluid in between the processes. It's only the change in volume, and change in volume is the cross-sectional area times the length of a certain tube. And if cross-sectional area stays constant, then it's just a change in the linear dimensions. And change in linear dimensions with respect to time, delta L, delta X, delta T is the velocity. So it's just how fast the fluid goes through a certain pipe or a tube. So your mass flow rate is the density of a fluid, cross-sectional area, and the rate of change in position with respect to time, which we call velocity, or speed if it's just the scalar magnitude. And here is your best friend for solving hydraulic engineering problems. It's called equation of continuity. It says that if no fluid is being added or taken away, and if the fluid stays the same fluid, then you can simplify everything to this little equation. Cross-sectional area of a tube in the first point times the speed of the flow of fluid at that point should be equal to the cross-sectional area at this another point times the speed of the fluid at that other point. So A1V1 is A2V2. This is the most common scenario for the majority of hydraulic engineering. You can always, well, you may just remember that the wider the opening, the slower the motion of a fluid. And if you narrow down the tube and the pipe, then cross-sectional area drops, so velocity has to go up. So going back to this diagram, see how V1 in magnitude is much less than V2 because A1 is greater than A2. So more cross-sectional area, slower motion. Less of a cross-sectional area, faster motion of a fluid. This is your bread and butter for any hydraulic engineering, or you being a doctor trying to figure out how fast the blood goes in veins, or whatever the fluid that runs through a certain pipe. Your equation of continuity is your best friend, and if there is a change in the fluid itself, then you have to consider densities as well. But usually density is the same, so you just cancel the densities and you're left with this expression. So wider pipe, slower flow. This is really like, you can't underestimate the importance of this expression. Please make a note, like one of the student learning outcomes from this whole hydraulic engineering part would be the equation of continuity. And sometimes you will hear the volume rate of flow. See, it was mass flow rate. Now it's volume rate of flow, which is just the product between the area and velocity, because area times velocity is what makes up the equation of continuity. For the majority of the problems in hydraulic engineering, you're going to put this as your first equation and Bernoulli equation, the conservation of energy principle, as the second equation, and you can solve pretty much everything that life throws at you. So Bernoulli's equation that we're about to discuss and equation of continuity, that's pretty much all you need for fluid dynamics. Okay, there's a pipe and the volume flow rate is given in certain units. What is the volume flow rate and the direction of flow for that unknown section? So you have number two, it's not number, it's the units. Okay, so the main idea is the overall volume flow rate cannot change. You can't destroy the fluid, and you can't get more fluid out of the blue. So let's see what's going on with this part of the pipe. You have to count all the inward fluxes, which would be what 4 is into, 8 is into, 5 is into, and 4 is into. So it's 4 plus a 5 plus the 8, that's what, 17, plus another 4. So it's 21 units into the pipe. Well, if it's 21 units into, then it's going to be 21 units out of. And you only have 2 out, and you have 6 out, so the total number of out is 8 units. So what you have for the remaining part of the pipe would be 21 take away 8, that's 13 units, and the direction is out. If there is any other answer, then this pipe will probably just blow up eventually because of the extra fluid intake, or it will just lose all the fluid because you're going to get more out than in. But if it's equilibrium, like the normal condition for a tube or a pipe, then there's got to be 13 units going out in the outward direction. That's the idea of a conservation. This is like conservation of matter. Remember, you can destroy mass. You can destroy electric charge. That's going to be the next semester. So for the volume flow rate, you have to keep the amount of fluid the same. Okay, on to the Bernoullis. as I said before, it is a conservation of energy principle, and you actually can go through the derivation process in the textbook. It's a step-by-step derivation, deals with work done by fluid to move a certain amount from point 1 to point 2, and then the change in gravitational potential energy if it's a different level of tube, if your tube goes up or down, and the kinetic energy of a fluid that you have to consider. So all things considered, you arrive to the Bernoulli's equation, which says what? You got your pressure at a certain point. You got the kinetic energy density, because there's density and it looks like kinetic energy, 1/2 mv squared. It's not m, it's density, but it's still an analog of kinetic energy, plus rho gh. Remember, it was mgh, now it's rho gh. So once again, you got kinetic energy density and gravitational potential energy through the density as well. And this total cannot change. Whatever is the point that you're talking about, point 1 or point 2, the combination of potential energy, kinetic energy, and the pressure at that point stays constant. So if pressure goes up, then one of the other parameters should go down, and vice versa. If it's the same level, let's say the tube, the pipe is just this, it doesn't go up or down, then your potential energy here and there is the same. So you just, get rid of potential energy and you only analyze pressure versus kinetic energy density. So faster flow, less pressure, which brings us back to the mass flow rate, greater surface area, slower rate. Slower rate means more pressure. This is the main connection. Once again, the greater the opening, the slower the flow. The slower the flow, the more the pressure. This is your bread and butter for hydraulic engineering. Fun fact, if you apply Bernoulli's equation to the case when everything is just at rest, you go back to statics, then velocity is just 0. So what do you have? You have a certain pressure plus rho g h, rho g delta y, rho g, a change in depth, if you will, which brings you back to the equation that we got from hydrostatic pressure. Let's go back and I'll show you that it's exactly the same equation right here for the barometer, right there for the manometer, and it was the same equation that we got for hydrostatic case in general. We got it from just basic definition of pressure before. Now we're getting the same rho gh from conservation of energy, which is a very satisfying conclusion. No matter which way you go from, you end up with the same equation. No matter if it's static or dynamic, you still have some reference results, which, makes it nice and smooth. Okay, water flows smoothly through the pipe shown, descending in the process. Rank the numbered sections to the volume flow rate. Volume flow rate stays the same. Remember, it's your equation of continuity that the volume flow rate is the same. Flow speed v through them. So now what's going on with velocity? With velocity, you think Um, you have to go back to Bernoulli. So greater velocity, less pressure, right? Greater velocity, less pressure. And greater opening, less velocity. Greater opening, less velocity. The opening is narrow, so velocity is more. So number one wins in terms of velocity. See how opening 2 is a little wider. So more A, less V. More A goes up, V goes down. So 2 loses to 1. For opening 3, well, it's the same. 2 and 3, they have the same opening, so it's the same velocity. And finally, number 4 is the widest opening, the greatest A, the least V. This is your equation of continuity that answers this question. And for the pressure is connected to velocity, so more velocity, less pressure. This is your Bernoulli equation. So see how it's 1, 2, and 3, and 4 for velocity, and it's exactly the opposite for the pressure. So greatest speed, smallest pressure. Smallest speed, greatest pressure. So that's the idea. Really nails all the possible scenarios. And like I said, the only thing you have to keep in mind is Bernoulli and equation of continuity. You can solve any pipe for anything that's missing just by going through those two equations. Now, there are very many applications of Bernoulli's principle, and there is a Torricelli's theorem that you see in the textbook. Really, just solve the Bernoulli's principle. See what's given, see what's missing, find what's missing through algebra, end of story. Really just plug in values and solve for what's missing. Airplanes fly only because of the Bernoulli's principle. See how there is the cross-sectional of a wing, and there is oncoming flow of air, and air travels greater distance on top of the wing versus a less distance traveled below the wing. So more distance in the same time means faster speeds. The faster the speed, the lower the pressure. The less the speed, the higher the pressure. And if it's lower pressure versus higher pressure, what do we know? There is a buoyant force acting upward from higher pressure all the way to lower pressure. Let's go back to this diagram that we had here for the buoyant forces. It's greater pressure, greater force at the bottom of the wing. It's less of a pressure, less of a force on top of the wing. So lower pressure, lower force, higher pressure, higher force. The force, the uplift force is produced because of the change in pressure. And also the area of a wing is also important because you have the wider area, you have greater uplift force. That's why those large airplanes, they have those large wings so that they can create the greater uplift force. Imagine there is no air going on top and the bottom. What's going to happen to the airplane? It's going to just plummet to the earth. It's going to crash into the earth. So that's why you have to keep that plane moving horizontally so that there is air, oncoming air, and the wing can produce this uplift force. If the airplane stops moving, it will stop producing that uplift force, the pressure on top and the bottom of the wing is going to be the same, and the plane is going to crash. That's the worst case scenario for pilots, when engines break down and there is no oncoming air that hits the wings of the airplane. Yeah, you can also measure how much of fluid goes through just by measuring the pressure, because change in pressure corresponds to a certain change in velocity. Bernoulli's equation. Here is a joke of the day. You can put it on pause in the video lecture recording and enjoy the Pascal versus Newton and meter squared. I'm gonna stop the recording here, and we're gonna do classroom discussion after a break.